So fantastic to see you all out here. I have a bunch of friends here. Hi, friends. Very excited to have you all here. We have, so a little stats on Yelp. We have 117 million uniques every 30 days. Gives you an idea of the data set size that we have to play with. So our first talk is going to be by this guy, Scott Clark, who's done some cool data wrangling with the rest of the ads team. And so he's going to tell you about this cool system that we have. Then we have John Billings, who's going to be talking about Elasticsearch and how we've deployed it at scale here. So with further ado, so Scott Clark has been with us for about a year and a half. He hails from, he got a PhD from Cornell, and he just got married. So big round of applause for Scott Clark.
Thanks, Mike. All right, sweet. So like Mike said, my name's Scott. I'm here working on the ads team on the targeting side, so trying to show those best possible ads. And so I'm going to talk to you about optimal learning for fun and profit. Quick overview, I'm going to talk about optimal learning, then two cool thought experiments within that domain, multi-armed bandits and Bayesian global optimization. So first up, what is optimal learning? Well, Warren Powell from Princeton, which is one of the fathers of the field, defines it as collecting information as efficiently as possible when collecting that information is time-consuming or expensive. And this could be time-consuming in the sense that it takes a long time to run an experiment, or maybe it's something like in drug trials. It takes a long time just to get the experiment up to the point where you can even run it. And it can also be expensive in the sense that you're running a drug trial and it takes a lot of money to go through that whole system. Or maybe it's expensive in the opportunity cost of running this experiment and showing users different versions of your site. So part one is going to be multi-armed bandits. And the way that this system works is, imagine you walk into a casino and in front of you is K slot machines. They're all set to free play, but you can still win money. Now, each one of these has an unknown and possibly different payout rate. I'm going to give you a fixed amount of time or a fixed number of pulls. I want you to maximize the amount of money that you can possibly get. So go. A little bit more mathematically, there's K random variables. At each time interval, you get to sample one, and then you observe the payout rate for that random variable. You don't get to observe any of the other ones. You just get that one. You want to maximize your expected total reward. So why do we care about this problem? This seems like just a crazy thought experiment. Well, it maps extremely well onto the click-through rate problem. You can think of each individual ad or search result as a bandit or as a slot machine, and you want to maximize the number of clicks. You can also use this for A/B testing, where you want to find the best solutions as fast as possible. You want to limit how often these bad selections are chosen. So this is a fundamental problem of exploration versus exploitation. Using the knowledge you already have about the system versus exploiting the knowledge that you could have. So with this, we can define regret, which is the difference between the optimal solution selected every time if you knew it for some reason versus the solution that you actually choose. And I'll note that anything that explores even just a little will have some regret, because in your exploration, you're going to choose something that's not perfectly optimal. But in the real world, you don't know the optimal solution from some oracle, so you have to explore. So I'll do a really brief example of a really naive policy for solving this problem called epsilon first. So we're going to sample sequentially just all the options for some fixed period of time. And we're going to only explore. And then after that, we're going to only exploit. Whatever was the best after that fixed amount of time, we're just going to hit that one over and over. So here's a bank of 3 slot machines. They all have unknown payout rate. I'm going to plot it above, but we need to learn what this is. So I'm going to sample a couple of times. Yay, oh no, yay, wee. Okay, so now let's exploit. So at this point, the middle slot machine looks the best. It's won every time. So from here on out to infinity, let's just sample that forever. Profit, right? Well, in this case, that actually works because we've accidentally selected the best one. It had the payout rate of 0.8. But what if the payout rates look like this? This is maybe a little less probable, but this is something that could actually happen. So now we've selected one of the suboptimal arms, and we're going to sample that forever. Well, now regret is unbounded. We need the amount of exploration to depend on the data. We need better policies. Thankfully, this problem's been around in academia for 60+ years, and hundreds of thousands of research hours have been poured into it. There's many, many, many different policies out there, and this is an active area of research. You can look on Google Scholar today and find papers that have been published in the last month on this very problem. Different policies work well in different situations. Some of them have bounded regret, like maybe logarithmic with the number of time. Some of it's linear. Some of it's sub-logarithmic. Different situations can call for different policies. And you can complicate this problem quite a bit. What if hardware constraints limit your real-time knowledge? The way the thought experiment works is you immediately observe that payout rate. What if you need to look through your logs to tell whether or not you actually won? Now you can only update your policies every day. What if the payoff is noisy or non-binary? What if we don't want to maximize clicks, but we want to maximize revenue? And that goes through some second price auction. What if you want to do parallel sampling, different policies with different parameters? If you're batching anyway, then you have this huge area to explore in between updates. Your arms can expire. The holidays are coming up, so holiday-related searches might be useful. But in July, maybe not. If you have knowledge about the user, you can have contextual bandits and pull them together. And then this problem gets further complicated if the number of arms increases. With 3, it was pretty simple because we just have to pick the best of 3. What if there's many? What if they're correlated? What if it's continuous? Every problem is different, and this is an active area of research. But the idea is to apply the best possible policy to minimize your regret in the metric that you care about. And this is a great segue into the second short example that I'll be giving, which is global optimization. What happens when there's a continuous parameter space and you're trying to find that optimal parameter? So the goal is you want to optimize some objective function. Let's call it click-through rate, revenue, average delivery time, some combination. You're given some parameters. They can be config values, parameters to your machine learning algorithm, anything. And you want to maximize click-through rate given those parameters. So click-through rate, or your objective, is a function of those parameters. Now, throughout the rest of the talk, there's going to be mathy stuff at the bottom. Most of the time, I'm not even going to reference it. In the bottom right, there's actual references that you can look up, or I'll be around after the talk to answer any questions you have. But feel free to just ignore it for now. So we developed such a system at Yelp, and we affectionately call it MO, or the Metrics Optimization Engine. It's a global black box parameter optimization system. Now I'm going to go through it in a telescoping level of depth. Here's the 10,000-foot view. History of how past parameters are performed. Mo does some fancy math. New optimal parameters. All right, so now 5,000-foot view. It wants to optimize some metric, like click-through rate, given the parameters as inputs. And then it wants to give you the new optimal parameters out. So you run some A/B tests with different parameters, feed it into Mo, and it gives you these new optimal values to A/B test with the highest expected return. Now there's a little bit of a naming convention problem here, where A/B testing usually means I'm going to show one version of the code to some users and a completely different version of the code to others. So you fork. This is more of an AA prime experiment, where you're showing the same code with just different parameters influencing how that code actually works. So here's an actual experiment. So sometimes on our biz details page, it makes more sense to show a little bit more ad content. We give an extra line of a little review snippet to inform the user about the business. Sometimes we'd rather show a little bit of distance information coupled with a slightly shorter review snippet. For different categories, this can have different playoffs. Basically, what we want to do is find the best cutoff for when we want to show that distance information and when we don't for every individual category. For pizza, maybe you want it really close. For movers, maybe you don't care as much. So we put in the parameters, and we give it the objective function, like it got this click-through rate, this whatever, feed it into Mo, it gives us these new parameters. Then we run MapReduce over the logs, throw it in some database. There's a lot of Python glue that kind of fits it all together. And then we shove it back into Mo. And you just iterate on this. And every time, it's coming up with these new optimal parameters that it wants you to try out. So why do we need to do this? Well, it takes a long time to do this naively. In the 1D example, you could just say, well, I'm just going to do grid search and find the best possible one. Well, you have to assume that it's linear or maybe at least monotonic, and then maybe you can do binary search or something. But grid search takes an exponentially more time with every dimension that you're throwing at it. This also becomes intractable to do manually if you want to optimize for every category, on every page, on every device, and things like that. The heuristics also quickly break down in the real world. The real world's noisy. Parameters can be confounding, they're dependent, they can be nonlinear. Many of them can be influencing each other at the same time. Mo solves all of these problems from the ground up in an optimal way. So how does it actually work? At the high level, it builds a Gaussian process with the information about the data we know so far. It optimizes the covariances of that, which is basically model selection. We know we want it to be a Gaussian process, which one? And then it finds the points of highest expected improvement. And then it returns those. And I'll break this down in individual slides. So Gaussian process, what the hell is that? So basically, it models every point in the space as a Gaussian. There's some mean and there's some variance. And every time you sample a point, it updates that. So as we sample this point here, all of a sudden, what we think the space actually looks like changes. And as we continue to model this space, as we continue to sample more and more points, we get a clearer and clearer picture about what it actually looks like. And then from here, we can inform the decisions about where we would want to sample next. So we want to put it into a Gaussian process. Which one? All three of these were built using the exact same data. These little X's are all in the exact same space. But we need to know things about like how relative distances matter. And so you have to inform things like the covariance between points, length scales, etc. All of these have different length scales, and some of them fit better or worse. An example being that BizDetails ad unit I was talking about earlier. It doesn't make sense to vary that cutoff by inches. At the same time, it doesn't make sense to vary that cutoff by 1,000-mile increments. You can overfit or underfit the data by doing that. So you want to find the maximum likelihood, the highest maximum likelihood Gaussian process that fits your data. Basically, what's the model given the data that makes the most sense? And this is a very difficult problem. So now that we have, let's say, some optimal Gaussian process that we think models our space, how do we know which point to sample next? Well, we want to maximize expected improvement. And that's saying we want to choose the point that in expectation will beat the best point we've seen so far the most. So we have our best point, and we want the new point to beat it by the highest amount. So when we have no information, all points are equal. But then we sample something. And then all of a sudden, what's on the right here is a contour plot of what would happen if, what the system would say would happen if we want to sample the next 2 points. So you can look at this. This is a contour plot. You can think of it as like a topographic map. This is the Sierras. These are mountains. These are valleys. Red's high, blue's low. Anything within the red value is higher, and then it cascades down. So basically, this point right here corresponds to sampling the point -1 and 0.5 roughly at the same time. And we expect to get whatever value this is higher than whatever the best point we've seen so far. If we only sample one point at a time, that's the same as restricting ourselves to the y=x line, which is saying I only have one point to give. What's the best one? Well, it looks like -0.5, so let's sample there. OK, we sampled there, and it did pretty well, but not so great. And now let's sample over here. So we do. And we can continue doing this over and over, but maybe we've kind of like oversampled this space. We can add in heuristics to say like, we're only bootstrapping this process right now. Let's explore a little on top of this expected improvement. So I notice there's a local maxima over here, which doesn't look so great, but part of that is because we just have no information. So maybe let's sample over there. And what do you know? We found something pretty good. In this case, we're trying to minimize, if you guys haven't figured that out. And then we just continue to sample over and over as this space continues to evolve. And we're constantly returning these best points to sample. In this case, I'm just drawing from the prior and saying, OK, I sampled this point, and I'm just pulling it from it. But in reality, this data could be informed from your logs. How many clicks did you actually get? What was the revenue you actually got for that parameter? And this could be the cutoff for where you're showing that ad. And it looks like we're finding a really great place right here. So as we continue to do this, we get more and more information. So this all is well and good. Lots of fancy math that I'm glossing over. Whole textbooks and field. There's a whole field behind this. But does it actually work? Well, Mo is live in production right now, and it's informing active experiments. And in every single experiment we've thrown at it, it's maximized the objective that we're giving it. Round over round, every time we feed something into Mo, we're getting something better out. And the great thing about this is it treats this underlying system as a black box. Parameters go in with some objective function, optimal parameters go out. It could influence almost anything anywhere in the stack, and it just treats it completely independently. So ongoing, we're looking at the best path towards contributing this back to the community if and when we decide to open source it. It's really cool math, and we'd love to share it. And then you can imagine the possibilities of linking these two systems together. Mo plus Bandits could help you iterate through the system as rapidly as possible for maximum possible gain and exploiting every single thing as much as you can in that exploration versus exploitation trade-off. And that's it.
Cool. Well, he's going to be talking about Elasticsearch and a really cool system that he and the rest of the search team have built here at Yelp. Folks in the back, if you could keep a little shh down, that'd be awesome. John, hand it over to you. After this talk, you'll be able to break up into groups. We have signs lining the walls, if you look, that actually indicate different teams that we have here at Yelp, or different focus areas. So we have an area for DevOps, or backend, or mobile, if you're interested in talking to team members at Yelp about those. So with that, I'll leave John to give his talk.
Thank you, Mike. So I'm going to be talking about using Elasticsearch to scale near real-time search. So, to begin, imagine it's Friday night, you're really hungry, you want curry, right? You want chicken tikka masala, in fact, and where are you going to go? You're going to go to Methil. You don't know whether it actually serves this dish, so you're going to use this little box in the bottom right-hand corner down here to search over this business, all the reviews, to see whether there's anything there. And quick plug, there's actually a delivery option if you need it. So onwards, you search, and you find that some reviews actually mention this chicken tikka masala. You're very happy. It's going to be a great evening. In fact, this one guy says, best chicken tikka masala of my life. Right, this place is fantastic. So great. How do we do this? Well, where are the reviews stored? They're stored in MySQL. There are many replicas, and we've got multiple data centers, but you don't need to worry about that. Basically, it's in a table in MySQL. How are we going to search over it? Easy, right? You're just going to use SQL. Right? We all know this, right? Select star from reviews where content like chicken tikka masala and ID is the business ID, right? Problem solved. Rainbows and unicorns, right? Any questions? No, actually, I'm joking. Because the kitten is not happy. It's biting us on the finger. What's wrong with this approach? I know there are some DBAs here. Mike?
Full table scan.
Full table scans are slow, yes. What else? Information retrieval. Come on, people. Any ideas? Say again?
Exact search. Yeah, you're doing exact search.
Yes, exactly. We want to do analysis.
Yes.
Indeed. So, pre-prepared. So we want to do analysis of tokenization, stemming, stop words. Performance is a real problem. We've got millions of reviews here. Highlighting and snippeting. You want to return maybe little fragments of text with the search terms highlighted. And faceting. Maybe you want to compute some statistics. Of all those reviews that mention chicken tikka masala, what's the average review? Okay. So here is where we start to use Elasticsearch. And we're using this in production for the system. And I'm going to talk about it now. So, imagine Elasticsearch is already running on a host. So here it is. We're going to curl this host, and we're going to curl this reviews_search endpoint, and we're going to give it some data. So we're going to actually not return any fields, but we are going to say highlight this particular field, review comment, and this contains the review data. And we're going to say, we're going to have a Boolean subclauses. One of them is subclauses. One of them is review comment must be chicken tikka masala, and one of them is the business ID must be 1, 2, 3, 4, 5, 6. Okay, it's easy, right? I mean, we can understand this. We're not hacking Lucene here. We're using a REST interface. It's not too scary. Okay, and then we get a response. And it took 10. That's not hours or days. It's actually milliseconds, so it's fast. So no full table scans here. And there are some shards. We don't really have to know what's happening here at this point. We're treating Elasticsearch as a black box. And we got some hits and some hit objects. And on to the next slide. These are what hit objects look like. There's an index type, ID, score. You can customize things like the score very easily. You don't need to do it out of the box. And there's this review comment, which is snippeted and highlighted, and it's working. It's easy, right? We've just whipped together a little search application with not much knowledge of any of these details. Onwards. So we're not actually going to be using the REST interface. So the Elasticsearch people have developed a couple of clients. There's the Python client, PHP client. Actually, I think there's Ruby. There's definitely Java. So you don't need to actually use the REST interface, but they're using it under the hood. It's a little easier if you use these libraries. So I just talked about how to search. We've actually got to get our data into Elasticsearch. And this is where we have to do a bit of systems integration effort because, you know, every system is a bit unique. Our data is in MySQL. We need to get it into Elasticsearch. We'd like to do this as quickly as possible because Elasticsearch offers near real-time search. So ideally, as soon as a review comes into MySQL, we want to be dispatching it eventually into Elasticsearch. And I think we manage, we do a good job. So it's complicated. We have some low latency indexes, some high latency indexes. I'll elide that detail. So what happens here? So how do we get data out of MySQL? What do we do? Well, we actually use triggers to watch tables of interest. And what a trigger does is it detects there's been a change to a table, and it inserts that event into another table. And what you can do in Gearman, you can actually listen to those events and put them in a queue, and then you have these indexer modules that I'm going to talk about in a moment that users have written, and these indexer modules get updates. And then they generate JSON documents, and they go to this black box Elasticsearch cluster. Okay, so what does an indexer module look like? Well, we've had to write this, and it's pretty easy. So again, you don't need to know the details of Elasticsearch to do this. So you as the developer, you write an indexer. You say, I'm interested in watching these particular tables in some hybrid Java, Python style. It's actually Python. So that's a list of strings. And you also say, what do you do when an event comes through on one of those tables? So you generate a list of indexing requests. And just to look at these two types, so an indexer event says what the table was, what the ID was, whether it was an insert, an update, or a delete, and a timestamp. There are things like replication delay. You don't need to worry about that as the user. And then you generate one of these index requests. And so you say, what index is this data going to go to? What's the document type and doc ID? I'm going to elide those a little bit. And what are the field values? So a mapping of field name to data to store in it. And that is pretty much all you need to do. So as a developer, you can ship this pretty quickly. And it's easy. Right. Okay, so what about things like sharding and replication? Right, this could take man-months to do normally. It's actually pretty easy with Elasticsearch because you say when you're configuring the index, I want to have 3 shards and 2 replicas. You can actually change the number of replicas on the fly. You can't change the number of shards on the fly. You'll have to create a new index and reindex to that. But you can change the number of replicas, so that can give you more read capacity. And it's easy, right? So what does a production dashboard look like? Well, you've got some indices here, and you've got some machines here, and each index has some number of shards, and you've got replicas across machines. And you can look at this dashboard and get a pretty good idea of what's happening. We've also got metrics dashboards to see in more detail what's happening under the hood. Okay, we don't just use it for finding reviews in businesses. We actually use Elasticsearch to power the serendipity feature, which on the mobile apps we use to discover local businesses. And so as a user, it's going to use data like what's the density of businesses around you, what's the time of day, so it can suggest great places to eat in the morning, so breakfast, or dinner places in the evening. It's also going to use details about your friends. And Elasticsearch is great for doing this sort of rapid iterative development. And this has been running in production for a number of months now, I think, and it's been great. So, we're done, right? Rainbows and unicorns, any questions? No, we're not really done, right? Because our data center is on fire, right? It is burning. Did we say, was it arson? I don't know, maybe it was self-inflicted arson, right? We didn't mind the gap, as they say in London. I don't know whether they A/B tested this. So kudos to Coda Hale. There's this concept that you've got in your mind an idea of what the performance should be, and then there's what's actually happening in production, and it's kind of hazardous, this gap. You can easily fall over. It's like, this is going to be very fine and fast. We're going to deploy in production, and everything's fallen over. Right. How do you stop this? Well, metrics are a great way to actually get more insight into your system. And also, what else can we look at? I don't know, it's gone. Anyway, onwards. Right, so here's an example of us not minding the gap. So disks are slow. So here's a ganglia graph, and we see that we get a lot of I/O weight as we enable something, and this is due to us running out of buffer cache effectively and having to go to disk for all our queries. So what can we do to fix this? Well, we can add more memory. That's a great thing to do. Or you can add SSDs. We've actually done that very successfully. Or you can scale out, so add more machines. And it's a business decision as to which you do. Okay, so here's another problem that we've run into in production. So there's this thing called field data cache, and when you're sorting on or fasting on a field, you have to load all the data in for that particular field into the JVM as distinct objects. So you run this sort of naive sort in production, and suddenly your JVM is choking because it's got so much data coming in and out of memories, and there are no rainbows or unicorns, right? So how do you do that? How do you stop this from happening? So test in stage and dev and look at your metrics. What else? So multi-tenancy. So Elasticsearch is great because it offers you multi-tenancy. You don't need to spin up a number of distinct Solr stacks, for example. But if you're in a multi-tenant environment, maybe you have a noisy neighbor who keeps you up at 2 a.m. listening to Metallica and arguing with his girlfriend. This is not cool. So how do you stop that? Well, you can vet your tenants before they're allowed in. So actually look over the code, see what it does, see what it's doing in dev, see what it's doing in stage. When it's in production, again, look at the metrics. And finally, if you do find you have a very noisy neighbor, then you can put them in their own cluster. And this is something that you just have to balance and actually look at the data. Okay. And with that, that's all. So hopefully you know a little bit more about Elasticsearch and a little bit more about how we use it to do rapid development here at Yelp. Thank you very much.